Hello, in this video, we're going to talk about linear systems of ODEs. This is a special case of systems of ODEs where they take on a specific form. So we consider a system of differential equations to be linear if we can express both of them in terms of a linear combination of the dependent variables. So we have two dependent variables, x and y. We have one independent variable, t, and we say that the system is linear. And this is the case that we'll study here, but this is what we call a homogeneous system. But this is definitely a linear system of the form ax plus by, cx plus dy. And for now, a, b, c, and d don't have to all be constants, but the mathematics gets considerably more difficult if they're not constant, so we'll focus on those being constant. So notice that we say that they're linear with respect to x and y. So you kind of look at this and you kind of see that y equals, or something equals ax plus by. It takes on the shape of a linear function, but keep in mind that the solutions are far from linear. We see powers of 1 on both x and y. Now, when we consider something like the Decoupled model, that model is not linear because there was that interaction term. It was the product of x's and y's that made it to be nonlinear. So the fact that we have x times y in there, that is not linear. That is not allowed in the form of the linear system. So you've got to be able to template match it to this form that we have here. Now, there are different kinds of systems. One of those variations of systems, one is called a decoupled system. And basically a decoupled system means that the rates are not dependent on the other dependent variables other than the dependent variable itself. So a particular example of that might be where, suppose we have two people, Bob and Ann, and Bob earns 10% on his investment and Ann earns 11% on her investment. Their rates of change in balance are, well, the change in Ann's balance per unit time is going to be 10% of whatever current balance is. Rate of change in Bob's balance at any given moment is going to be 10% of whatever his balance is. And so we can see that this system is decoupled because if we were to actually do a little bit of drawing and we were to kind of represent these two systems, we see that that Ann's, we kind of represent these as states, that Ann, her balance is only autonomous, it's independent on it, or dependent on itself, and Bob's balance is only dependent on his own balance, not on Ann's as well. So the rates are only dependent on the variables themselves. So we call that system completely decoupled. Now solving it is pretty straightforward. You can separate variables on one equation. So Ann's balance would be of the form k1 e to the 0.11t, and Bob's balance would be some other constant e to the 0.1t. Done. There's the solution. We also have systems that are called partially coupled, and a partially coupled system is one rate is potentially dependent on the second dependent variable, but at least one of the rates is independent of the other dependent variables. So, well, let's take a look at this example. We have Lake 1, which contains 50,000 gallons of water. It takes in a contaminant at a constant rate of 3 grams per day, and water exits at 100 gallons per day. So we're going to assume that the inflow and outflow rates are the same. So we can, and then suppose that water leaving Lake 1 enters Lake 2. So right away, what we have going on here is a system where we have Lake 1, and we'll just say L1 represents the lake itself, and I have some contaminant flowing into this lake at a rate of 3 grams per day. Now that's already a rate of change in the chemical itself, so we don't really need to know what the flow rate of water in is, but we're assuming that it's the same as what's coming out, so the volume is not changing. So that output we're saying is going to actually flow into Lake 2. We have what's called a cascading system, and so whatever comes out of L1 goes into L2, but then water feeds out of L2 and we don't really know where it goes after that. So that's unimportant, but the rate of change in L2 depends on depends on L1, because what's coming out of here is what's going into L2. But in order to know what's going on in L1, we don't really need to know anything about what's going on in L2. This system right here is independent of this one over here. So we have we'll call these, let's say, C1 and C2. So let's see. C1 is the amount of chemical in there, so maybe I'll change this to C1 and C2. And the chemical coming outside is going to be C1 grams per the 50,000 gallons of water multiplied by, so that's grams per gallon times gallons per day, which is 100 gallons per 1 day. And so there's our outflow rate, there's our inflow rate, that's already in grams per day. And so we see that what's coming in here is 3 grams per day. And again, this rate is in grams per day, much like many of the problems we faced before, grams per day minus grams per day. But the inflow, what's coming into C2, it's nice here because what's coming in is exactly what's leaving C2. So the inflow term into C2, into Lake 2 is 100 C1 over 5,000. It's just a positive version of it because what's exiting here is what's coming in here. And then what's coming out is dependent on what's already inside. Well, there are C2 grams at any given time per 60,000 gallons multiplied by the outflow rate. We're assuming that basically everything's consistent and flows out at a rate of 100 gallons per day. And so we get our outflow term there as well. Now we see that this is partially decoupled because C2, the rate of change in C2 depends on both C1 and it depends on C2, but the rate of change in C1 only depends upon itself, and that's where we get the name partially coupled. You can kind of think about them as they're somewhat married, these two systems. One depends on the other, but the other doesn't depend on the first. Now, the solution gets a little bit more tricky because we can't really solve dC2 dt until we have solved the first one. But the good news is what we can do is we can solve the first equation, substitute C1 into the second equation and then solve the second equation. So it's like we kind of get to use the independent system, a portion of the system, and then we'll use that to help us solve the next part. So we'll assume that initially the amount of this contaminant in the lake at time 0 is 0 grams. So we begin by doing the Laplace transform, same as usual. S Laplace of C1 minus the initial condition, but the initial condition is 0. So I'm not even going to write that term. Laplace of 3 is 3 over S. And here we have to be careful because, again, C1 is our dependent variable, so this is really minus 1/500th C1. So factor that constant out, I have the Laplace of C1. Now I'll move the negative 1/500th, I'll add that to both sides, and I have factor out in L of C1, I have S plus 1/500th times Laplace of C1 equals 3 over S. And now I can divide both sides by S plus 1/500th, and I can use partial fraction decomposition formula to get that. And now I see I can invert that right there. That's just the constant 1. That's the function e to the negative 1/500th t, and I have the multiplier of 1500 out front, so both the constant 1 and the e to the negative 1/500th, which is negative 0.002 if you wanted it as a decimal. So what I see is going to be happening here over time, if I were to think about this graphically, is to the concentration. Well, initially it's clean, and at time 0, e to the 0 is 1, so I'll have 1500 minus 1500, I'll have 0 grams initially. But what I see that happens over time is this portion here is going to decay very rapidly. So that means this whole term is going to go to 0, and in the long run, all I'll have left is the 1500. So I kind of see that something like this will happen if I were to graph this function, and it'd be asymptotic to 1500. Now, if you wonder why it's 1500, you only need to look as far as that's 1500 grams per, let's see, what was the amount of water in that? I think it was 50,000 gallons of water. And that fraction, 1,500 grams to 50,000 gallons, that should be, I need to be a little bit careful here because I've reduced things. So this is 1,500 grams per 500 gallons because I've reduced down fractions and stuff. So 1,500 grams per 500 gallons is actually a 3-to-1 ratio, which makes sense because I'm inputting this contaminant at a rate of 3 grams per day. So therefore, eventually, the concentration of water in the first lake should reach the saturation point, which is the amount that's coming in. It can't exceed that because that's the concentration coming in is 3 grams per gallon. Sorry, I take that back. Okay, well, let's come back to this. We'll come back to this a little bit later. I think I'm just making things up here. The point was to solve this. So now what I'm going to do for the second system is I now know what C1 is equal to. So I'm going to make a substitution. So I know that C1 is equal to, let's see here. We simultaneously make this reduction. I've canceled out a couple of zeros here to make it simpler to work with. So we have 1500 minus 1500 e to the negative 0.002 t over 500 minus c2 over 600. Now we notice that this function is in terms of t and c2. So what I can do is do a little bit of work on this. So 1500 divided by 500 is 3. 1500 divided by 500 is 3 e to the negative 0.002 t minus c2 over 600. So now this is basically a basic Laplace transform. The Laplace of C2 is S Laplace of y minus C2 of 0, but we're assuming that both lakes are initially clean, so the initial condition is 0. Laplace of 3 is 3 over S minus 3 over S plus 0.002 minus 1/600 Laplace C2. Should probably watch my notation. And so now when I move 1/600 Laplace C2 to the other side, factor out a Laplace of C2, I have my typical form. I have my S plus 1 over 600. I'm going to divide both sides by it. And of course, now I have two situations where I need to do partial fraction decomposition. So the first part decomposes into 3 times 1 over 1/600, which if you do the math on that, you get 3 times 600 is 1800, times 1 over S minus 1 over S plus 1/600, that's the decomposition, plus 9,000. So that comes from the fact that if I take the difference between, I'm kind of mixing fractions and decimals here, 1/600 minus 0.002, 1 divided by that multiplied by 3 gives me 9,000. 1 over the first factor minus 1 over the second factor. And so now I can easily invert this. I get 8,000, which is the inverse of 1 over S is 1, multiplied by 1800. And then inverse of that is e to the negative 1/600 t, and 1800 times that. Inverse of that is e to the negative 0.002 t, multiplied by the 9,000. Inverse of that is e to the negative 1/600 t, multiplied by 9,000, gives me the minus 9,000. And I can do some simplification here. I can combine these two terms here and get whatever that is, negative 2,700 e to the negative 1/600 t. I'm good with the way it is. And again, I want to kind of think about what's going on here. This is going to achieve a different amount of the chemical. I can see that at time 0, this term will be 1,800, this term will be 9,000, this term will be 9,000, and the positive and negative values offset each other to give me an initial value of 0. Okay, well, so in the long run, these three terms will approach 0 because they're decaying, and so in the long run, I'm going to have an asymptote here of 1,800. Okay, and so the thing I wanted to point out is that these two lakes approach different saturation points. One approached 1,500, and the other approached. Let me open up a new Desmos here real quick. And so if I take the saturation point of the first lake and divide it by its volume, I get 0.03. Now that's grams per gallon. 1,800 divided by the volume of that lake, which is 60,000, is also the exact same concentration. So what this illustrates is that even though those two lakes are technically, reaching different amounts of the chemical, because you have this water flowing back and forth through these two lakes, you end up getting basically you have this type of system here going on, and some of it's flowing out. So eventually they'll reach their saturation point. So in the next example, we'll take a look at, well, what if these systems are not partially decoupled?